Hello everyone, I'm Norman Walber, and we've been talking about infinitesimal approaches to calculus with an algebraic flavor, coming from the dual complex numbers over a general field. And now I want to show you how this avenue opens up the idea of calculus over finite fields, where our usual intuition about smoothness and rates of change and so on are debatably maybe not so evident. But nevertheless, there's very rich phenomena, and I want to illustrate some of this rather with some examples. So we're not going to go through an entire theory, okay? The theory will be laid out in my algebraic calculus courses. The Algebraic Calculus 2 course will cover this material and much more in considerable depth. And to prepare yourself for that, you can access Algebraic Calculus 1 right away and get cracking and learn about that. Okay, so we're going to illustrate things with a specific finite field F7, which we've already talked about, elements 3 bar, 2 bar, 1 bar, 0, 1, 2, 3, where the bars represent negatives. So this is the same as -3, -2, -1. And in other treatments, we might call this 6 and this 5 and this 4. I just prefer to do it this way. It makes things a little bit more symmetrical around the central element 0. And the operations are addition, multiplication, subtraction, all mod 7. And can we really do calculus over such a finite field? Yes, we can. But we need to reorient our thinking a little bit. In some sense, what we have to do is return to a more 18th century approach to functions. Okay? The 19th and 20th century approach was more set theoretical, more pointillist. The 18th century practitioners like Euler and Lagrange, and maybe even going back to Newton and Leibniz, had a more holistic or more algebraic orientation to what a function was. And we need to make a little bit more contact with that, with this kind of new approach of polynumbers center stage. The modern notion of a function as something which takes an input of a certain kind and gives you an output of a certain kind pervades so much of modern mathematics. But it actually is not really the only way of thinking about these things. And I want to illustrate the importance of shifting your point of view, especially when we make contact with this finite field kind of analysis. You're going to see directly why we need to retreat a little bit from the all-importance of the functional point of view. So here are the polynumbers, 1 alpha, alpha squared up to alpha to the 8, and we're going to just look at what their values are. So we're going to evaluate these things on the elements of our finite field F7. Okay, so there's are the elements, and here are the evaluations of these polynumbers on these elements. 1 just evaluates to 1. Alpha is just like the identity, so you just get the input back. And then here's alpha squared. So 2 squared is 4, but 4 is the same as -3, so we write 3 bar. 3 squared is 9, but 9 is the same as 2 mod 7. And then alpha cubed. Things become simpler with alpha cubed. 3 cubed, for example, is 27, which is the same as -1 or 1 bar. 2 cubed is 8, which is 1. 1 cubed is 1. Note that this is a kind of an odd thing, so that the symmetry around 0 is an anti-symmetry at this row here, while with the even ones, like alpha squared, the symmetry is a pure symmetry around there. Okay, that's one of the advantages that you get by working with this representation of a prime field. Okay, and so I've just listed them. You can check, just take 1 of 2 and take powers of 2 and reduce the mod 7. And what you see notably is that when you get to alpha to the 6, it becomes quite simple. So the 6th power of anything is 1, unless you're starting with 0. The 6th power of 0 is, of course, 0. But the 6th power of anything else is equal to 1. And this is a very special case of the famous theorem of Pierre Fermat. Okay. Now, that has the consequence that then when we go to the next level, like alpha to the 7, we're just multiplying alpha to the 6 by the original guys. That means we're actually going to get exactly the same values as we did with alpha. So there is then a repetition here, okay? For alpha to the n is the same as alpha to the 7n for any n in F7. So as functions on the field, alpha and alpha to the 7 are indistinguishable. Okay? This is not something that happens over like the rational numbers or the real numbers, if you believe in them. This is a new phenomena that really only appears in the finite field story. But at the level of polynumbers, the polynumber alpha is not equal to the polynumber alpha to the 7. Why is that? Because the polynumber alpha is a vertical list of numbers. It's the vertical list 0, 1. That's what it is. And alpha to the 7 is also a vertical list of numbers. It's 0, 0, 0, 0, 0, 0, 0, 1. Okay, it has 7 zeros above it. Alpha has 1 0 above it. So as polynumbers, these are definitely distinct. But as functions, they are exactly the same. So here is this very important thing to think about and get your head around, that when we're doing calculus, we have a choice of whether we should be working with the function values, like looking at the actual values of the function, like the graph, or whether we should be looking at just the algebraic form of the corresponding polynumber. Which of them is actually primary? And Euler and Lagrange would have said, well, the polynumber is primary. Modern analysts would say the function's values are primary. We're taking the position of Euler and Lagrange here, okay? It's the actual algebraic entity which creates the function, which is primary. And we can see that because when we look at our yoga of derivatives, the derivative of alpha is 1. Remember Faulhaber's definition. You just take the exponent, you bring the exponent down, and you lower the exponent. So the derivative of alpha is 1. And what's the derivative of alpha to the 7? Well, you take the 7, you bring it down, so it becomes 7 alpha to the 6. Now in this finite field, having a 7 out front here means that you have 7 of these things, and 7 of anything is the same as 0 of anything. So this is 0. Okay. So notably, the derivative of the polynumber alpha is 1, while the derivative of alpha to the 7 is 0. So when it comes to differentiation, the calculus wants to work at the level of polynumbers, not at the level of function values. Admittedly, this takes some getting used to if you're, trained in classical calculus, because you're used to thinking about the graph of a function and everything depends on the graph of the function. Okay? That's not the case here. It's the actual algebraic form of the function which derives the calculus. So a lot to think about here, a lot to think about, and to appreciate this difference between the actual polynumbers, which are just these algebraic identities, and their representations as functions, which are sort of shadows of them, but the shadows do not capture the full polynumbers themselves. And the calculus wants to work at the level of the polynumbers. So I want to have a good look at a very specific example here so we can really see what's happening. I'm going to look at a rather interesting curve called the semi-cubical parabola, which was first introduced by Leibniz, I think, and then interesting properties were discovered by Neal. It, in classical calculus courses, has this as its defining equation. Y equals x to the 3/2. Okay, and here is its graph. Okay, actually, there's sort of two branches of it. Maybe you might think of this as like there's a square root implicitly here, so you're kind of taking positive and negative values of the square root. The shape of the curve is actually better appreciated if you move away from this transcendental description and go to the algebraic description, which is y squared equals x cubed. So from my point of view, this is much, much preferred. Okay, this in fact doesn't really make sense because you can't actually evaluate this thing. So if I ask you, what is the value of this thing at x equals 5, you can't actually give me a complete and correct answer. So as far as I'm concerned, this is not a valid function. It's just something that you're writing down, but it doesn't really correspond to an exact pure mathematical object. While this thing does. This is an equation just involving, basic algebra. Y squared equals x cubed. That's a curve. And here is a graph of it. Okay, now in classical calculus, you might be interested in the derivative of the slope of a tangent. So here's a point A on it, say x, y, and there's the tangent to the curve. And to get the slope of that tangent, well, you want to differentiate this, and the standard story is that the derivative of this, you still apply the same kind of rule, even though that it's not really a polynomial, but you still the same rule applies. The 3/2 comes down, the 3/2 lowers up here to give us 1/2. So we're talking about 3/2 of the square root of x, which itself has to be contained in quotes, because this itself is, again, something that you can't actually calculate. So it looks like a function, but it is not really an honest function. It doesn't actually give you an output. That's correct. Okay, why is this curve interesting? For a number of reasons. It was actually the first curve of this kind to be sort of rectified, so some kind of formula for an arc length was discovered by Neal. But it came about with Leibniz's question of finding a curve which has the property that if you have a particle rolling down it, okay, that the particle has a constant vertical velocity. So if you just looked at its vertical component, it would be going down with constant speed. Okay. Now, notably, that's for this particle here. If you looked at rolling down this part of it, that would be different. It would get going faster and faster, but in this direction, it has constant vertical velocity. So it's quite interesting, and it's a cubic equation that has an interesting singularity, a cusp singularity. So it's actually quite a pleasant curve. And we want to ask, does it make sense to talk about such a curve over a finite field? Can we ask calculus type questions about this and get reasonable answers, even over, say, F7? And absolutely remarkably, we can. And it's really beautiful. So let's consider this semi-cubical parabola over F7. Here's the equation that we're going to be generalizing. Y squared equals x cubed. So here is the plane over F7. Okay. X coordinates from 3 bar up to 3, y coordinates from 3 bar up to 3. So every point here is represented by one of these boxes. Okay, so for example, this box here is the point 0, 0. That's the origin, and that's obviously on the curve. In x's here, I've shown you all the points of the 49 that lie on the curve, that satisfy y squared equals x cubed. Let's have a look at what they are. So A is 1, 1. That's 1 in the x direction, 1 in the y direction. That's this point here. I might actually just give you their names, because that's going to be a little bit important as we proceed. B is 2, 1 bar. So 2 in the x direction, 1 bar in the y direction. That's that one there. There is B. C is 3 bar 1. 3 bar 1. There it is there. D is 1, 1 bar. 1 bar, that's there. That's D. E is 2, 1. That's this one here. And F is the remaining one. 3 bar, 1 bar. There it is there. There's F. So there are 7 points on this semi-cubical parabola. And, at first it doesn't look very much at all like the one over the rational numbers that we can draw. And you might think, well, how can we ask any kind of question about, how can we ask about, areas associated with this, or slopes of tangents? Well, it turns out that the tangent to this curve at A, okay, is a line, and I've actually shown you that line. It's the line with the little green squares. So the tangent to the curve at A actually has this equation, 3x minus 2y equals 1. You recognize it. It's a linear equation. It represents a line. It corresponds to these points right here. This has a kind of a linear aspect, especially if you kind of think of this thing as sort of repeating, this pattern repeating, so that this thing going down in this direction is really kind of like coming down like this, and then it comes back up there. It's almost like a torus. Okay. So that's the tangent to the curve at A, and I just want to observe at this stage here, and we'll just remark this for later on, that this tangent also happens to meet the curve at another point, which happens to be B. All right, so the tangent at A also happens to pass through B, but it doesn't pass through any of the other points on the curve. Now let's do some infinitesimal analysis with this curve. And we're going to use the fact that it is a de Castelnau-Bézier curve. This is a very, very important class of curves in calculus, even though most calculus courses don't even deal with them, but they're a very important class, which are the curves which are polynomially parameterizable. Okay, so this curve is parameterizable by this rule here, that gamma of t, say, is t squared equals t cubed. That's going to satisfy the equation y squared equals x cubed. Now that's in terms of sort of a parameter, or sort of an input t, but we can also express that in the world of polynumbers by introducing this curve gamma, which is a pair of polynumbers, so alpha squared and alpha cubed. We could call that, say, gamma of alpha. That's a way of thinking about parameterizing this thing here with some polynumbers. And we prefer to work in the world of polynumbers rather than in the world of actual functional evaluation. Okay, so let's take this polynumber curve here, okay, and let's replace alpha with alpha plus an infinitesimal. How do we do that? Well, we make the shift to the dual complex numbers and polynumbers by polynumbers over the dual complex number, like I was telling you about in our last video, okay? So we're going to replace the alpha with alpha plus beta epsilon. And now we're thinking about all of these things, if we want to be formal, as actually sort of 2 by 2 matrices. So they're actually polynumbers whose entries are 2 by 2 matrices. The 2 by 2 matrices are dual complex numbers. Okay, so this is alpha plus beta epsilon squared. This is alpha plus beta epsilon cubed. When we expand this out, by now familiar kind of thing happens. We get alpha squared plus 2 alpha beta epsilon, and the higher powers of epsilon are 0 because epsilon squared is 0. And similarly here we get alpha cubed plus 3 alpha squared beta epsilon and no higher powers of epsilon. And then by our derivative theorem we see that, well, this thing here is capturing the first polynumber alpha squared as occurring right there, and over here is its derivative times beta epsilon. There's the derivative of alpha squared appearing. And over here we're talking about alpha cubed. There's alpha cubed there, and here is the derivative of alpha cubed times beta epsilon. So that matches up with what we already should expect. Now we can think about this in a kind of a vector form. We can think about this as being the point alpha squared alpha cubed that we're starting with, plus a multiple of a certain vector. Okay? The multiple will be beta epsilon, because that's the common feature here, and the vector will be the vector with components 2 alpha and 3 alpha squared. These are just the derivatives of these things. And I like to use this notation that in the affine plane we represent points with square brackets, we represent vectors with round brackets, and we are allowed to add a point and a vector to get another point. So in the classical picture, if you have some curve gamma like this, and there's gamma of alpha, the picture that you might have in mind that is that this vector that we're obtaining here is a direction in the tangent vector to the curve at the point gamma of alpha that we're considering. That's the picture that you would have in mind, at least in the sort of continuous world over the rational numbers, say. So this gives the direction vector of the tangent line at gamma of alpha. This is a way of getting at the tangent line using infinitesimals, which doesn't involve any secants or limits, because over a finite field or over a general field, we don't have those things available to us. But we always have this purely algebraic approach. It's more powerful. So this is the kind of description of the tangent line that we've obtained. We are at this point a squared, a cubed, say actually on the curve. And then the tangent line to that will be lambda times 2a, 3a squared. So we're now going down to an actual explicit point on the curve and an explicit tangent line. And we might be interested in trying to get a linear equation for this parametric equation. So the x-coordinate of this would be a squared plus lambda 2a. The y-coordinate would be a cubed plus lambda times 3a squared. And then to get an equation involving x and y, the idea would be to eliminate the lambda. I'm going to leave this to you as an exercise, right? To take these two equations and eliminate lambda to get an equation purely involving x and y, but no more lambda. It'll still have a involved, and what you'll get is 3xa minus 2y equals a cubed. And crucially, that works only if a squared is not equal to 0. If a happens to be 0, okay, then this whole thing degenerates to a certain extent. We have the origin over here, but this vector that we get is the 0 vector. So there's no real tangent line here. Okay? So we have to exclude that from our analysis, and if we do that, then we get this equation. It's a linear equation in x and y, 3xa minus 2y equals a cubed. That's then the equation of the tangent line to the curve at the point a squared a cubed that we've obtained through this infinitesimal analysis. Okay, so we've done this algebraically. Is this line, however, really tangent to the curve? At the point a squared a cubed? What does this mean geometrically? What does it mean algebraically? All right, so this is not a complete course in these things. I just want to give you, enough information so that you should be able to follow the reasoning. More detail, etc., in the algebraic calculus course. So let me try to explain how we want to think about tangents from an algebraic point of view. We do not want to think about a tangent as being a limit of a secant. Okay, that's involves this infinite process of taking limits. We don't want to do that. So how do we get around that? So to understand that, let's look at a simple example, okay? Much simpler than the semicubical parabola, just the ordinary parabola y equals x squared. And let's choose the simplest point, the origin. And let's try to understand what makes the x-axis, the line y equals 0, a tangent. Obviously, geometrically, it's a tangent, but what actually makes that a tangent? So let's consider a vector, okay, emanating from the origin, a particular direction. We're going to look at a direction. And just to be organized, let's take some multiple of 1d. The vector 1d has 1 in the x component and say some d in the y component. So it's some vector, okay? And let's consider x and y, in this case here, being somewhere on this line from the origin determined by 1d. So we're looking at all the lines through the origin, actually all of the lines except for the vertical one, all the lines through the origin, and we want to sort of understand what happens as we go along these lines. And particularly we want to figure out what's special about this horizontal line. What makes this one a tangent line and this one not a tangent line? You might at first think, oh, it has to do with the way the line intersects the curve, that this thing here intersects the curve at this other point. Okay, so this curve here, this line intersects the curve at 2 points. And you might say, well, that distinguishes this one. This one only intersects the curve at 1 point. That's correct, but it's not exactly correct because this line here also meets the curve in only 1 point, but it's definitely not a tangent. So we need something stronger than just meeting the curve at 1 point to get at the notion of tangency. Okay, so let's have a look at this general situation. We're moving in this general direction. xy is lambda times 1d. So that means x equals lambda and y equals lambda d. So suppose we wanted to know which points on this line actually lie on the curve. Well, we would want to plug these things into the equation of the curve. We can write that as 0 equals, say, g of xy is x squared minus y. So that's a function of two variables which expresses the curve. So if we replace x with lambda, we get lambda squared there. We replace y with lambda d, we get minus lambda d there. And then this thing here factors as lambda times lambda minus d. And we want to set that equal to 0. So under what conditions can we solve this? Well, we can always solve. There's always a solution, lambda equals 0. And that's sort of obvious because the line that we're choosing passes through the origin. We know that origin is a point on the curve. So typically this has a single 0 at lambda equals 0. So this equation, if we're solving it for lambda equals 0, there's a single 0 at lambda equals 0. Unless d equals 0. Okay? If d happens to equal 0, then this expression is lambda squared, not lambda. And that's telling us that in this case there is a double 0. Okay? So the point is that the horizontal case is algebraically captured by this condition of the intersection being given by a double zero rather than a single zero. That's an algebraic way of capturing what tangency is in a relatively simple example. And now let's do a similar analysis with the semi-cubical parabola case. We started at the point a squared comma a cubed. We computed a potential tangent line, okay? And we now sort of want to check whether it satisfies this nice algebraic criterion that a tangent line should satisfy. So let's take the equation of the curve and write it as g of xy equals x cubed minus y squared equals 0. And going back to the earlier calculation, here was the x-coordinate of the point on the tangent line that we got, a squared plus 2 lambda a. So we have to cube that. Here's the y-coordinate of that. That was a cubed plus lambda 3a squared. To square all of that. And then what happens? We cube this. We get the first thing cubed. That's a to the 6 plus 3 times a squared squared times 2 lambda a plus 3 times a squared times this quantity squared plus 2 lambda a all cubed. And then we have to subtract the square of a cubed, which is a to the 6, twice the product, which is 6 lambda a to the 5th, and the square of the last term is 9 lambda squared a to the 4th. So we have to subtract all of those. What do we get? The a to the 6 cancel. Here there's 6 lambda a to the 5th. That cancels with that one. Here there's a to the 4th. How many? There's lambda. There's 3 times 2 squared. That's 12. And here's minus 9 lambda squared a to the 4th. So a total of 3 lambda squared a to the 4th. And finally, 2 lambda a all cubed, which is 8 lambda cubed a cubed. Common factor of a cubed comes out. Common factor of lambda squared comes out. And we're left with 3a here plus 8 lambda here. Okay, so what is this telling us? We're looking for an intersection between this potential tangent line that we found, which was parameterized by lambda, seeing when it actually hits the curve. In other words, when this thing is 0. And we see that there's a double 0 at 0. The actual point when lambda is 0, which is the initial point that we're starting with, a squared comma a cubed, that is a double tangency. That lambda squared there is telling us that. Right? So that line that we found with the infinitesimal approach really does satisfy the algebraic condition that we want a tangent line to have. But this calculation also shows us something else that's interesting, that if we're looking at points where this line meets the curve, there will be another solution when this term is 0. So there's another 0 when lambda equals minus 3/8 of a. And that point will then correspond to this point. Here's the starting point, a squared a cubed. Here's the lambda that we're now considering, minus 3a over 8. And here's that vector, 2a, 3a squared, that we found with the infinitesimal approach. And when we calculate this, we have a squared here minus 3/4 of a squared, so that's a quarter of a squared. And we have a cubed minus 9/8 of a cubed, minus 9/8, so that's a total of minus 1/8 of a cubed. So that's then a formula for the additional point on the curve which this tangent line at this point meets it at. Okay, and we can rewrite this as minus a over 2 all squared and minus a over 2 all cubed. So this really is another point on the curve, and the parameter, instead of being a, it's minus a over 2. So we learned that if we're looking at the tangent at the point on the curve which is parameterized by a, that tangent will meet the curve at another point whose parameter is minus a over 2. So let me summarize some of the formulas that we've found. That the curve x cubed equals y squared over a field f, actually quite a general field, has tangent line 3xa minus 2y equals a cubed at the point a squared comma a cubed, provided a is not equal to 0. So that's the equation of the tangent to this point on this curve. And this tangent line further meets the curve at an additional point, and that additional point is minus a over 2 all squared minus a over 2 all cubed. And our calculation actually was very general. Okay, it was purely algebraic, and so we can expect that this works over a general field. Now, if we go back to the F7 case, where we've actually seen the 7 points lying on the semi-cubical parabola. And so now we can see that this hexagon, actually it's an oriented hexagon, A, B, C, D, E, F, has actually a very nice connection here. That this is both an inscribed and circumscribed hexagon on this curve. Namely, these 6 points are all on the curve, but also, in addition, the tangents at these 6 points to the curve are exactly these lines. The lines AB, BC, CD, DE, EF, and FA. So I showed you the picture in one of our earlier slides of the tangent at A, and you saw that the tangent of A also goes through the point B. So that's a direct consequence of a computation that you can just do, mod 7, exactly using this formula here. But correspondingly, the tangent at B also passes through C. The tangent at C passes through D, the tangent at D passes through E, the tangent at E passes through F, and the tangent at F passes through A. So if you draw these lines joining these points successively, then you're getting a hexagon which is both inscribed and circumscribed in the curve. So I find this quite interesting. You might like to think about whether you can cook up a curve in the regular rational plane that also supports a hexagon with this rather remarkable property. So we see that when we're looking at the finite field situation, number theoretical issues are going to appear in the calculus. Okay? Some of these things are happening here because we've chosen F7, and 7 is a small prime which has certain, very pleasant properties. And if we had chosen a bigger prime, well, we wouldn't expect that this thing closes up after 6 points. We might have to go further. Okay? So number theoretical aspects of whatever prime we're working over will impact on the geometry and the calculus that you can expect to have over that finite field. So calculus is actually a much broader, much bigger subject than I think is currently appreciated. And you see this by adopting an algebraic point of view, which importantly allows also an infinitesimal approach that in some sense justifies the initial intuitions of the great 17th and 18th century mathematicians. In the next video in this famous math problem series, we'll have a look at the 4-color problem. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.